Hi everyone, we are DeepQube and we're using deep reinforcement learning to solve the 2x2x2 Rubik's Cube. Next slide, please. So this problem is interesting because even the 2x2x2 Rubik's Cube has over 3.6 million possible combinations. And finding the optimal solution given an initial combination, which we call a scramble, is an NP-complete problem. So machine learning is like a different, interesting approach to this problem. Specifically, reinforcement learning gives a large is a possible use because it has a large state space and finite actions. And to us, it's basically an introduction to reinforcement learning. Next slide. So the input to our model is essentially a flattened down representation of the cube. So we assign each color an integer and we flatten it into a 24/1 tensor. And then in the next slide, we'll see that we basically give a one-hot encoding to give a final shape of 24/6. Next slide, please.
I must apologize. Tony dropped off the call, so I'll take his part. So this is kind of our strategy for solving the cube. We split it up into two parts. So you can see first we use reinforcement learning to just solve the first layer, and then we use supervised learning to solve the rest. Our reason for doing this is we tried to use reinforcement learning to solve the entire cube, but this turned out to be difficult due to a combination of lack of computational resources and our lack of time mostly. And as we'll discuss later, reinforcement learning, it's difficult to design reward signals. Next slide, please. So this is our reinforcement learning model, a brief introduction to reinforcement learning. Basically, it's a field of machine learning where you take an input to some sort of environment with finite actions, and then you try to maximize some notion of reward. In our case, that would be solving the Rubik's Cube. So as you can see here, basically we have an MLP that goes into a cube simulator, which we wrote in Python. And then it outputs a reward signal in a new state, and it continues to learn to try to maximize the reward, which of course is solving the cube. Next slide, please. Now for the supervised learning portion of our model, we have a data set that maps states to moves and then allows the agent to determine which move to do given the state for solving the last layer. Next slide, please.
So in order to train our reinforcement learning agent, we actually created a scheme we call graduated learning, where the agent tries to solve the first layer in parts. So you can see it first learns to solve half of the first layer, and then it moves up to 3/4, and then the full thing. Next slide, please. So in terms of data, we use scrambles that are randomly generated from this program called tnoodle. And essentially the training scrambles is what the agent tries to start off from and explore to solve. And then the graduation between those three layers that we talked about earlier was based on if it's able to complete 100% of the validation scrambles. And then finally, our results are based on the test scrambles. Next slide, please.
So as I mentioned earlier, we had a separate data set for supervised learning. How we did this is we found all possible scrambles that already have one layer solved, and then we went to the AlgDB database to find solutions to those scrambles. And then what we did is we reversed the solutions, which allowed us to create that data set of mapping states to moves. Next slide, please. So for our results, our baseline model is the layer by layer method of solving the 2x2 cube, which is a beginner's level method that anyone could learn. To check for optimality, it's known that any state on the 2x2 cube can be solved in 14 moves or less. This is known as God's number. And the last thing is the reinforcement learning portion of our model is actually on par with competitive human solvers, which is pretty interesting. Next slide, please. So this histogram compares our baseline model to DeepQube and the optimal bound. I'll point out a few things. Obviously, DeepQube is much more efficient, solving in 21 or 22 moves on average. Additionally, there's less deviation, so DeepQube is a lot more consistent with than the baseline model. And we have a few solutions below the optimal bound, but for the most part, DeepQube is non-optimal. Next slide, please. Now here, we did have an issue where the reinforcement learning portion of our model fails in certain cases. So this is just showing that we have a 4% fail rate when it's unable to solve the first layer. Next slide, please. So this is an example of a scramble that DeepQube was unable to solve. As you can see, the arrow denotes two pieces that need to sort of be swapped in place. You can think of this as being like close to solved, but not quite solved. And this is difficult to solve because you'd need to take the pieces out of the positions they're currently in and then put them back into place, which is a lot of extra moves compared to more common scrambles. And interestingly, this is the same kind of scramble a competitive human solver might classify as difficult. Next slide, please.
So some learnings and improvements that we could potentially make from next time if we do the project again is that first we'd use the orientation agnostic state representation. As you can see, the two pictures of the Rubik's Cube are actually the same, but have a different orientation. Our current embedding would be different. There's GPU speed isn't everything, and our reward functions and intermediate words can cause our model to repeat moves. And also the reinforcement learning is slow, and we should avoid early termination, like after a couple of thousand epochs. Thank you.
Great. Really interesting. Well, really great introduction in 6 minutes to reinforcement learning to provide context for all this. And I really love how you dove into the problem and tried to solve it. I think that's fantastic, actually. It's a good engineering instincts. And you gave us hints of what's going on. I sense it's more complex than even what you showed. So really well done. One quick question. I guess I didn't quite understand when you switched over to a supervised learning, you kind of got to it, but how did you do the supervised learning for the second half of the cube? Can you just restate that? I think it's up here somewhere.
So essentially, we used reinforcement learning to solve the first half of the cube, essentially, and then the second half,
that's what I'm asking about. Is
the second half was done using supervised learning, and this is essentially we try to get the neural network to learn how to map one specific state to a move, because there's only 675, I believe. There's specific numbers above, but there's only like very few comparatively states. So we thought maybe we can use supervised learning to figure out these last few moves.
But what I'm asking is how is that done? I didn't understand that. I want to know what the inputs are.
It's a little difficult to explain without actually reading the code, but basically what you can see is like this would be a specific state, for example, and then the solutions we got out of that database that would tell you that the first move is supposed to be turning the right layer counterclockwise. So then we would map.
The input is the state and the output is the next move, correct?
Yes, we would map this state to a move.
That's all I needed to say. And you know the answer because you've got that data set. That's really interesting. And then that worked, you're saying?
Yes, and we figured that was a good way of doing it because there were only 675 states, which are actually all derived from like a smaller set of 40 states, just with like doing an extra move before or after. So really it was just a matter of writing a couple Python scripts.
Cool. And is there a reason you couldn't solve the whole thing this way?
I can comment on that. So essentially, like, we didn't like fully get, because we kind of ran out of time, but the reinforcement learning training is really slow, and like,
you are trying to answer my question, right?
Oh, Tony, I think Professor Rose is wondering why we didn't use supervised for the whole.
I'm not asking. No, I'm not asking why you didn't. I'm just asking to speculate. Could you use it for the whole problem?
Supervised learning.
You could, but I believe the solutions would be less efficient. And also it would be very difficult to generate that data set because you're starting, like if you tried to start from the beginning, there would be so many states that you would have to, input the solutions to have those known solutions to create the supervised training set.
Yeah, when I read about it and hear about AlphaGo and all that stuff, that it was, they're dealing with Go and chess and stuff like that, and they use pattern matching in like a CNN to take some guesses at things. So maybe it's possible. Right. That's the interesting thing about this. I was just curious. One point you said, where is it? Right here. You got some below optimal. That sort of defeats the definition of optimal. Can you help me out there?
Yeah. So I'm realizing a bit that that line is a bit deceiving. So there should actually be a histogram mapping the optimal.
Okay, that's
it would
fine.
make the most sense. So the majority of solution, like
Yeah, that's fine. That's the answer.
yeah.
I mean, optimal is a very pure and simple thing, and just saying below optimal is, doesn't work.
Yeah.
So, but you're saying it's not a constant. Yeah.
Yeah, a lot of like 11 move solutions would be considered optimal, for example. Yeah.
11 as opposed to 4.
Like anything below 14
I
is
see.
in that consideration.
I see. So don't use that word.
Yes. Yeah.
Yeah. Okay. Wei, any quick comments? Sorry, that was great work, by the way, guys. I found the presentation really interesting. What do you have, Wei?
Right. Just saying that supervised learning, you can call that imitation learning. So that it's closer to reinforcement learning. Just really just imitation learning. Yeah, essentially you have a target from the expert. Yeah, so it's just the terminology that makes your project sounds better because that still falls under the umbrella of reinforcement learning. And yeah, for this diagram, the baseline, I still didn't catch it. Like, what is the baseline for this? If I missed it.
So the baseline model is just like a hard-coded if-else implementation of the kind of solution you would find if you went on YouTube and searched how to solve the Rubik's Cube. It's basically what a very, very naive human would do.
I see. All right, cool.
So procedural. Great.
Yes.
Any questions or comments from anyone else?
I thought the project was really cool. I'm just wondering, like, would the efficiency be a lot better for the last layer if you just implemented a lookup table, or was it predicting the like optimal last layer solutions from that data set? Because it sounds like it's a pretty feasible thing. So it's 635 states, right?
Yeah, so it's the neural network is essentially a lookup table in this case. Although like we didn't have time, I wanted to try some generalization afterwards, like see if it was able to figure out some certain patterns and figure out how to solve it given less like of the data I was training on. Yeah, but unfortunately we kind of got stuck on time and
So you're saying it could be a lookup table.
yeah, right now it's a lookup table.
Yeah. And if we're to extend it to like larger cubes, which had like more states after one layer solved, then it could be potentially more efficient to try. Like also Rubik's Cube is like a type of combinatorial problem that can be kind of extended. Like you could potentially use the neural network as like a pre-trained, like a transfer learning thing to work on other similar types of combinatorial problems.
Okay, we better move on.